right, if everybody's ready, I think we should get started so that we can stay on time today. Welcome to this presentation and thank you for coming. My name is Thib Guicherd-Callin. I am with the LOCKSS program at Stanford University, more specifically Stanford University Libraries. And a lot of what you're going to hear about today is a particular storage application as viewed from the very niche angle of a library or memory organization. So first, brief show of hands, how many of you have ever heard of the LOCKSS program or LOCKSS technology or LOCKSS as part of storage? So a typical turnout, 1 or 2 people in an audience. So we are a now 20-year-old software and library outfit. There are not that many programs that are using the same technology over a 20-year period. And I have been with the program since 2005. And if you have been on the conference circuit, maybe at IIPC or PASIG or other storage-related venues, you may have encountered my 2 predecessors, Vicky Reich and David Rosenthal, and they speak very eloquently about the problems of storage as they apply to libraries, especially research libraries and other memory organizations and archives. And I'm more new now that they are retired. So the first thing that you'll see about me is that I'm not as seasoned to the contest circuit as other people because I don't have a LinkedIn, I don't have any business cards, so I'm sure we can figure out ways to connect without all that. So here is an outline of this presentation. It'll have 5 short parts, and I reserve some time at the end for questions and answers. If you have any questions during the presentation, please feel free to catch my attention, and we will see whether a timely answer is good or if we should delay the question until the end. So first, I would like to take you through a very brief context and use cases section to put some context around where the LOCKSS program comes from. So the LOCKSS program comes from libraries. It originated at Stanford University Libraries, more specifically at Highwire Press. Highwire Press was the first outfit, starting in academia, now its own spin-off business, that had the idea in the mid-90s that perhaps we could put scholarly communication, like journals, on this newfangled thing called the web, and maybe that would be a good way to disseminate scholarly and scientific information. And as this developed in the late 90s and early 2000s and continuing into today, there was immediately a big shift of power in the world of libraries and scholarly publishing. In a traditional research library, the library operates on an ownership model. So there are many independent replicas, many independent copies of books or journals. This is real objects. And this has a lot of features. So for example, this is disaster resistant. So if one library catches on fire and everything is destroyed, there are many other replicas elsewhere at other libraries. It has disaster recovery properties. So if something bad happens to a copy, more copies can be made, maybe by making a photocopy if it's a book or a journal article, or through well-established, centuries-old interlibrary loan programs. It's tamper evident, so this is not an application that many people think about when they think about storage, but in the world of realia, of real objects in libraries, there are actually very dedicated groups that make it their mission to seek out every copy of a work that they disapprove of and rip out certain pages or destroy them from libraries and going to each library and trying to get rid of each physical copy of a work. That's one sort of more extreme example, but another example would be government document information. So for example, the US government sends the transcripts of Congress and the courts to hundreds of libraries across the country in a program called the Federal Depository Library Program. And occasionally they say something, the US government says something that they regret and that they have to officially correct. And when that happens, there's a process. They have to recall a document from every library, and usually that's for typos or things that are not too embarrassing, but occasionally it can be somewhat embarrassing. And when that's done, of course, no librarian will ever send back the document without asking questions. They make a photocopy of it before they send it back. So it's tamper evident. There's essentially no way to recall something from a library system. And it offers permanent access. So the goal is to offer access to the information over the long term, usually longer than the lifetime of people. So when scholarly publishing went on the web, this model was completely upset. So now we have a leasing model. What ends up happening is that the publisher, maybe Elsevier or another large publisher of scholarly materials, has a website and the library or the university subscribes to it, usually using the range of IP addresses that they're coming from or some other authentication mechanism, and they pay a monthly or annual fee, usually quite a hefty one, to access the protected areas of the publisher's website. So essentially there is a single master copy now that is being leased. If the library runs out of money and can no longer afford to subscribe to a particular journal, let's say, or publisher, it's not like before where they have at least the volumes that they purchased on the shelves. Now they probably have nothing. The terms for post-cancellation access that publishers make available are usually really iffy about what the means of access after you no longer subscribe on a regular basis are. Another misfeature of this is disaster recovery. So what happens if the publisher goes away forever? Maybe they burn down to the ground, or they have a catastrophic event at their data center, or they just go out of business. What do libraries, what do memory organizations have stored that they can make available to their patrons or local community? That model with a single master copy is not temper evident either. On the equivalent of the Federal Depository Library Program, where government information in the US is kept. This would apply to other countries as well, of course. Now there isn't a paper copy that's being mailed out to different libraries. There's a website of government information. You can, for example, in the US, go to gpo.gov and find all of these transcripts and government information. Well, what if someone were to change a word on one document, for example, from is to is not, or is allowed to is disallowed, or whatever? Who would notice? What processes are in place for that tempering to become evident? And what kind of permanent access do libraries have in this model? Well, it depends on the iffy terms of service for post-cancellation access that they might have with scholarly publishers. Again, this is sort of in the realm of libraries and how libraries felt at the turn of the century. So, people at Stanford University, within Highwire Press and then later within the greater library system, created LOCKSS, which stands for Lots of Copies Keep Stuff Safe. And the goal of LOCKSS technology was to build software that would enable libraries, especially research libraries, most especially for scholarly content like journals and articles and ebooks, to reestablish the old ownership model so that they would have something on premises if they no longer have any money to pay for a subscription, or if the publisher goes away, or to detect tampering and all of that. So basically to go back to the features of the old model of real objects that the libraries were used to. So what has LOCKSS technology been applied to? Well, so far it has been very academia-centric, very library-centric, very research-centric. So the first application of LOCKSS technology was what we now call the Global LOCKSS Network, or GLN. It is over 100, probably more like 150 research libraries all over the world, mostly North America, but also in Europe, Asia, and South America, that together, as a group of 100+ libraries, are preserving the copies of electronic journals and scientific journals and electronic books that they subscribe to as research libraries. So this is mostly university stuff, scholarly communication journals. Later, some of the publishers, the very large commercial publishers, think the Elseviers, the Springers of this world, some of them were big enough that they did not have to bend to this desire from research libraries, even really large and powerful and rich ones, that they had to improve on this leasing model that they had unleashed at the beginning of the century. And they were happy to continue doing that leasing model from the single master copy without participating in an initiative like the Global LOCKSS Network. But that does not mean that they did not in fact worry about the longevity of their intellectual property. For a large publisher, that intellectual property is quite valuable, And they themselves found the need that they wanted to preserve their own stuff. It's just that they didn't want to allow each and every subscriber that they had to have a local copy on premises. So they got together and formed the LOCKSS archive. LOCKSS stands for Controlled Locks at the time. And the LOCKSS archive is a dark archive. So it uses LOCKSS technology to preserve scholarly, again, sort of similar scholarly electronic content like journals and ebooks. But that archive is not meant for public access at all. It's a dark archive. There is no access until a catastrophic trigger event happens. For example, when a publisher goes out of business forever and no other publisher catches their holdings or their intellectual property for cents on the dollar. If content is unavailable from any source that used to participate in the LOCKSS archive, it is then taken out of the dark archive and made available on the internet for everybody. And then LOCKSS technology became of interest to other preservation communities, still mostly academic, I would say, nothing too business or corporate yet. Just as I mentioned, there were some properties of libraries that were of particular interest to people who preserve government documents and who are interested in the tamper evidence and the transparency aspect that had. And that transparency was starting to be eroded by the disappearance of programs where government information was shipped physically on paper or on some other medium to libraries and instead is available over government websites. So now for researchers and citizens alike, librarians were very interested in applying LOCKSS technology to government documents. And so that was done. There are at least two preservation networks now using LOCKSS technology for government documents, one in the United States and one in Canada. With interest from other sort of national consortia. And then other regional and national groups of memory organizations, maybe archives, state archives, national archives, university systems that are in a country where sort of like the university system tends to be nationalized, became interested in LOCKSS technology to preserve also their scholarly materials, but maybe also government information, and why not records, for example, historical records or national archives of various kinds. And ultimately, it became apparent that LOCKSS technology, though it had been developed for the very strict application of libraries, especially research libraries, the technology underpinning it wasn't really related to libraries or journals or anything serial in nature. It could be applied to any kind of electronic data, and so there has been a renewed interest in LOCKSS technology in recent years. So these slides will be available on the website and through other channels through the conference. So you don't need to write these long URLs, but I just want to give you, for context, 4 key publications that describe the underpinnings and reasonings and protocols, et cetera, that are sort of behind the LOCKSS technology. So what we call the founding paper dates back to as early as 2000 at Usenix, and it is by Rosenthal Reich, and it's called Permanent Web Publishing. There is then 2 twin papers that we call the protocol papers by Maniatis and other authors, which date back to 2003. And even though there have been some slight changes and refinements to the LOCKSS protocol, the LOCKSS Content Audit Protocol since then, ultimately the very large legacy of the LOCKSS system is still based on that research paper from 2003. And another paper that I will refer to also is called the Threat Models paper. So in 2005, the LOCKSS program couched a lot of its assumptions on storage systems and the design of a storage system that is meant to be a digital preservation system. I'll come back to the definition then in just a second, was couched in this paper on the threat models facing digital preservation systems. All right, so let's talk about these threat models. So digital preservation is an art, not a science, that's practiced by a very particular kind of customer or end user. And that end user we like to refer to under the umbrella term memory organization. And a memory organization is likely to be something that you think of as a library, perhaps a university library or a research library. Maybe it's going to be a regional, state, or national archive. Maybe it's going to be a museum, some kind of institution that is interested in the perennity of data over a very, very long period of time. And in the LOCKSS program's view, a digital preservation system is one whose goal is to preserve the information it contains and keep it accessible to users over periods of time much longer than the lifetime of individual storage media, of hardware and software components that it may comprise. And also, I guess, a bit of an unspoken assumption in this definition that I didn't include in the slide is also much longer than the lifetime of actual users, so the lifetime of the people that are using the system. So think the kinds of things that a library is doing, the kinds of black box storage system that a library might be interested in. So there are three key properties to a digital preservation system that we think are important. In our model, there is no single point of failure. It should have no single point of failure. So for example, it must tolerate the failure of any individual component because of course it's going to be made of various components. And in general, these systems should be designed to tolerate more than one simultaneous failure. The second key property of a digital preservation system will be that media, hardware, and software are going to flow through as they fail or are replaced. So it is going to be expected, and this is sort of like the Google model of farms and farms of server. In the early 2000s, this was a bit of a novel idea, but commodity hardware, there's tons of it, it fails, you replace it, the system doesn't fall over just because one particular thing is down at the moment or has failed. And finally, you want to strike a balance on the regular audits so that they are frequent enough to keep the probability of irrecoverable failure acceptable, but that's balanced against what is an acceptable rate of failure of a system like this, a system that is meant to last over more than one lifetime of any one component. So the paper sort of describes a taxonomy of threats that are part of the sort of the model for building the LOCKSS system. This first sort of slide is all of the ones that I guess would be under the category of when things die or when things break. So media failure, for example, storage media is expected to fail and degrade with time, which causes irrecoverable bit errors. Hardware is going to fail, so components must be expected to suffer either transient failures like power loss or irrecoverable catastrophic failure, such as a burnt-out power supply. Software is going to fail, so for example, we must expect the system to tolerate the fact that software bugs are going to creep in and occasionally affect the data, are going to occasionally alter or put at risk the data. Communication errors. So a digital preservation system can't assume that the network transfer that is being used to communicate is going to be perfect. So when the content is being circulated between nodes in the system, or when the content is being ingested into the system over the network, there is no absolute guarantee that that is going to result in perfect transmission. Failure of network services. So this is a bit of a broad one, and it goes beyond just on its face that the network is down. So what happens to the system when the network is down or when two nodes in the system can't communicate? But it also includes things like the underpinnings of the network services. So for example, an excellent example would be DNS resolution. What happens if in 10, 20, 30 years a particular domain name that used to resolve to a particular thing doesn't resolve anymore? URL shorteners, what happens when URL shorteners go away? So we rely on them to name things. They don't mean anything anymore. What happens when those systems fail or go away, et cetera, et cetera. Natural disaster, I like to call this catastrophic disaster because natural disaster like earthquake, flood, fire, et cetera is one aspect, but I guess it could also go with things like war is kind of one that would happen and that I wouldn't qualify to be a natural disaster, but sort of a large-scale catastrophic disaster. Then there's a second category of threats that a digital preservation system that is of interest to libraries would have to fight against, and this is the category of obsolescence. So media and hardware obsolescence. Not only are we expecting media and hardware to fail over time, but we're actually expecting that something else is very likely to happen before they fail. And that thing is that even though the media or the hardware has not failed, there is no longer any viable player or reader for it. So that can be a software problem or a hardware problem, and there are numerous excellent examples in the literature about sort of media obsolescence happening even though the hardware is totally fine. There is just a disconnect and one of the pieces in the chain is broken, and so there's no way to read the material. Software obsolescence is also something that is of interest to libraries. It manifests itself as format obsolescence, for example, when a format is no longer in vogue. So the original material is in a format that no one has good software to read anymore, and things of that nature. A third category is when, I would say, when people fail. So operator error, someone might accidentally unplug a machine or wipe it and not remember that it's part of a network of preservation or that it's communicating with other people. Economic failure, and that one of the 13 I think is sort of almost probably the highest one that libraries care about when designing a storage system that is useful for their particular applications. And it is the fact that libraries are just perennially underfunded. And that their forecast for how much more they're going to be funded in the future is usually a negative number or a negative percentage. So they must work with the fact that they're building a system for the long run that is expected to run out of steam over time economically. This also goes under sort of organizational failure. Libraries are part of other organizations that usually have their own agendas, like libraries and government. And so even though the system might be working well, it might be fighting the forces of organizational politics and organizational degradation around them. And finally, of course, a system of that nature needs to resist to attack. So attacks being either external, so that would be the electronic equivalent of the people who disagree with a particular work and have set out to destroy every copy available, for example, or an internal attack. Someone might be trying to bring the system down from the inside. Yes?
What about a discovery attack? Say, when you search for Tiananmen Square, you get no results, even though within your world, you're still doing everything right. Is that a threat that you account for? Or?
Yeah, I mean, so I think that I would put this under sort of failure of network services. You mentioned sort of a search result that returns no results, but even though there are results, right? So I would put that under that category, but this could be part of...
But the answer will be the network's working just fine.
Yes, right. The system is working just fine, and yet there is a threat, and that threat is caused by an external factor in this case. Or, yeah.
Probably in your category 4 there.
Yes. Sure. So that can be an external attack, in this case, say, a government-sponsored attack, or, right, something to that effect. Yes, sure. So libraries and archives are facing all sorts of threats that are much beyond simply media failure or hardware failure. I mean, those are important failures as part of their threat model, but they are interested in sort of niche and unusual threats. So the LOCKSS technology started out as a system that was very library-centric, so it was sort of a single software stack that applied to libraries and that libraries would find palatable, that they would install on site, run on a commodity appliance, usually just commodity hardware with cheap hard drives, and then each library that has this software installed is talking to all the other libraries, so that's what we call the global LOCKSS network. Nowadays, of course, we make sort of like ad hoc preservation networks that aren't worldwide. But at the time, the idea was, all the libraries in the world are going to unite and do this together. And so the LOCKSS Content Audit Protocol is a sophisticated cryptographic protocol in a peer-to-peer network where the nodes in the network call each other periodically into opinion polls and through a cryptographic hash prove to each other what they have and that enables them to have a paper trail for them to provide repairs to each other in the future if a repair becomes needed, for example, when damage is detected at one site, or when there's catastrophic failure and a particular node loses all of its content, and so forth. So LCAP stands for LOCKSS Content Audit Protocol. I'm going to go through a very basic example here. I invite you to read the literature for all of the nitty-gritty details. Let's imagine 6 peers in this preservation network. I'm naming them P1 through P6, so 6 peers. Originally, they have a piece of content that I'm going to call X. In many applications, this would be just an object, but in the particular applications that libraries care about, this is actually, X is not a single thing. It's usually a large group of things, and you can address individual objects within it. So it might be a whole collection, a journal's worth of, a year's worth of journal content, an annual output of a publisher's ebooks. I mean, it might be a large collection. But right now, all the peers have identical copies of X, and peer P1 calls an opinion poll on X. So it asks the others what the hash of X is. They all compute, since they all have exactly the same thing, they happen to come up with the same answer, H1. And so P1 can remember that P2 through P6 had agreed with it on X at one point. At a later time, P2 does the same thing. It also calls an opinion poll on content X. Now, here I'm representing sort of like the same 6 peers, so that could be one application of LOCKSS technology, sort of a closed network with a small number of peers. But this could be in a context where there is an open-ended number of participants in the peer-to-peer network. So each opinion poll doesn't have to be with the same 6 people, right? This slide could be with 6 completely other people that P2 is talking to. But for the sake of argument, let's say the same 6 peers. It does the same thing. What's the hash of X? They still all agree on X, so they all say H1. So it remembers that P1 and P3 through P6 have agreed with it also on X. So that's what we call landslide agreement. Well, now P1 incurs some damage, some bit flip, loss of hard drive, sector goes bad, whatever, operator error, erases a file. Someone from the inside is attacking the system and trying to erase that from peer P1 on its storage system. So that's what I'm representing here as sort of like a different color. So now it thinks that's X, but it thinks it's blue instead of gray. All right, so what is the hash of X? Everybody else agrees among themselves, so they all say H1. And for some reason, P1 thinks, oh no, I think that that's H2. So that's landslide disagreement. Everybody else agrees together, but I disagree with everybody else, so I must be wrong. So when that happens, there's a repair request. In the applications that we care about in libraries, usually you can obtain a new copy from the original source. You would go out to the website that the particular object came from, and you would get a new copy of that journal or issue or article. But if that is no longer available, then you need to rely on the other peers to repair. And, P2 remembers that P1 had agreed in the past. So P1 had proved to P2 through this hash that it had the same thing. So it's okay to provide a repair to P1. It's not just trying to steal the copyright content. And so X goes from P2 to P1, and now all of the peers agree yet again. So there are 3 main states in this system. What I demonstrated here was landslide agreement and landslide disagreement, right? So, you know, the steady state is everybody agrees exactly on everything. The typical sort of hiccup is one peer starts to disagree with the others, but all of the others still agree among themselves. So that's landslide disagreement. But of course, there's all this spectrum in the middle of inconclusive agreement when one or more of the peers have a bit flip or have lost their content, or maybe they didn't get exactly the same copy, or right. So now there's inconclusive agreement. So when there's landslide agreement on your opinion poll, you take no action and you're pretty confident in that outcome. When the agreement is inconclusive, you still take no action, but you raise an alarm because that's not normal. That is a departure from the normalcy of the system. And that's because you don't really know what to think when there is no consensus among your peers on whether they all agree together and I'm wrong, or I'm definitely right and all the others are wrong, or whatever. So you have low confidence in this outcome, but you take no action. And landslide disagreement is when you seek a repair, and you also notify the user so that if you got a repair that was actually fraudulent, someone is trying to convince you, repair for me, get this piece of content for me, you still notify that you have repaired so that you could detect that, well, it wasn't supposed to repair, it was working just fine, so what happened here? And you have a high confidence in that outcome. And when you're the attacker, you want to cross this valley of confidence from high confidence on not taking action through low confidence and a state of alarm to high confidence in repairing, meaning altering your copy of the content, but you have high confidence in this, and so the attacker has to cross this gap in confidence, and that the protocol is designed to make this very difficult without getting noticed. So I'm going to go through 3 quick slides here on, just bullet points on some of the niceties as part of the protocol that make this, of course, more attack resistant. The little diagram that I showed was a vast oversimplification. The polls aren't literally on the hash of the piece of content that you're trying, on the object that you're trying to compare. It's actually salted each time with, for each pair of a poller and a voter with sort of a piece of unique data called a nonce, one sent by the poller, one sent by the voter. They all have to compute the hash value, including these nonces, so that there are no replays, so that you have to expend computational effort to stay in the game if you're a bad guy and you're trying to convince other peers to repair a bad copy from you. You are going to have to expend extraordinary computational effort to stay in the game without getting nonces. So there are systems where no 2 nonces may be the same within long periods of time, and so forth. Repair verification. So this applies to other aspects of the threat model. Byzantine fault. Yes, well, P2 is providing a repair to P1, and it turns out that over the network, as it sends the repair, and a bit flip happens, or someone is eavesdropping and altering the content, so when it gets to the other end, it isn't actually the thing that P2 was sending to P1, so there's vote verification. So when you get a repair, you verify it. Okay, so here is one of the most, I think, sort of curious features of the LOCKSS system and the LOCKSS protocol, the LOCKSS Content Audit Protocol, that is usually baffling in other applications, other storage applications. So a lot of storage applications that have a self-healing mechanism are interested in physical fixity. So physical fixity is what I like to call sort of like the exact sequence of zeros and ones. Is it the same as what I meant originally, or is it different? And if it's different, then it's diverged and needs to be repaired to the original sequence of bits. But that's actually not a very common case in the original use cases of the LOCKSS system, which was web preservation. Now, nowadays the LOCKSS system is being used on data that doesn't change over time, so there is a physical fixity of the object over time. But many applications of the LOCKSS system in academia are actually where none of the peers, or at least not all of the peers, but even none of the peers have a byte identical copy of the content. And yet that content is the same, just the same under some other definition than the bit sequence on disk, or the bit representation. So the typical example of this is you are a research library, you subscribe to the Journal of the American Medical Association, and you want to preserve it over time. When Stanford University goes out to the web to see an article, at the top left it says, you are logged in as Stanford University. And when you're at Harvard, it says, you are logged in as Harvard University. So no 2 peers at any time actually obtain the same byte sequence of content, even though they're accessing the same thing, the same object, retrieved at the same address, that's understood by all to be the same object. So the LOCKSS system actually has a fairly sophisticated system of plugins. So that's sort of like domain-specific knowledge that you introduce into the system to say, yes, these 2 things are the same thing if you remove this dependent bit and if you cut out all the ads and you find them in such and such place and so forth. So it is possible, and in fact, we started out that way. It was the norm when we started out, and nowadays, as it gets applied to other types of data, it's not as much the norm. That none of the replicas are identical, and yet this protocol can be used and has this plugin system in place so that this cryptographic hash can be apples to apples, even though the objects are not apples to apples. So you might say, well, then what happens when a repair occurs? if the copy is not actually an exact replica of the one that was lost. So there are two answers to this. There's no replacement in this system, only a new version. So it's only sort of like non-monotonically, it's only monotonically increasing. So the old copy is not lost. And also in that instance, for example, well, what that would mean is that if Harvard gets a repair from Stanford, there is one web page in the archive maintained by Harvard that actually says Hello Stanford on it, but that is not considered by that particular domain-specific plugin to be loss of meaningful data to the archive. All right, so you know, for time I'm going to skip through this, but we could have a discussion about sort of how does the LCAP protocol help with these various threats from our 13 threats in the threat model that libraries care about. So this is, of course, sort of like obvious for how this deals with media failure and hardware failure and software failure, and how it has some aspects for natural disaster recovery, but also how does this fit into a model that libraries care about of organizational failure and economic failure? How does it resist to external attack and internal attack? And that's sort of more cryptography and math stuff, which unlike my predecessors at the previous presentation, I am not, I don't have the background to discuss, and I'll have to refer you to the literature. So we are at a developer conference, so I would like to sort of give an insight into what it means to work with the LOCKSS system, because as I mentioned at the beginning of the presentation, hardly anyone knows about us in sort of this particular crowd. And so the original audience of us was research libraries. Our target was web content in particular. The context was an appliance model where each peer was going to participate by having its own single machine with its own sort of commodity hard drives attached to it. So this was all a monolithic stack. The only way to preserve any piece of content with the LOCKSS system for a long time was for that piece of content to enter the LOCKSS system at one end and be preserved all the way through by all the components of the LOCKSS monolithic software stack. Of course, as more use cases developed and more people became interested in the LCAP protocol, but not in all of the bibliographic data that surrounds libraries, we made it a priority to engage in a new initiative to modernize our software, first of all, and to also sort of unlock the LCAP protocol from this monolithic stack so that it can be embedded into other systems without you inheriting the entirety of the system and having to preserve that piece of content through the entire stack of LOCKSS. We are in the middle of a 2-year Mellon Foundation grant to help us with this re-architecture. The goal will be sort of web services, REST services for which there's an API. We're also taking this opportunity to modernize our software because you might imagine that a piece of software with a 20-year legacy has some arthritic things in it that are a little creaky. So we're more than happy to use this opportunity to modernize. Here's a diagram that is not necessarily meaningful to everyone in this audience, but this is sort of, if you think of the monolithic LOCKSS system of days before, there would be a big black box around all of this, and that's the LOCKSS system. Data enters at one end and comes out the other end, and all of these components are inside. They're just not separate, and it's difficult to interact with any one subcomponent. And the goal of the re-architecture is to make these components independent so that you might run some of them or all of them, or you might switch out the kind of database that you're using underneath or whatever, as opposed to this sort of like monolithic product. So this is the current state of the re-architecture. I've included, again, no need to sort of write down all these, but you know, GitHub URLs where you can go to see the 5 inaugural sort of REST APIs that we have for services. The one that is of interest to people will probably be the Polar service, which is the one that sort of runs this LOCKSS Content Audit Protocol between peers. And in each one, that's the sort of notation at the bottom, for each one, you go to the develop branch on Git, and inside this file, there is your YAML file that you can plug into your favorite tool to generate a client stub in your language of choice. And software assets available include Maven Central jars, this is all in Java, so Maven Central jars that you can include in your own project, or Docker containers that run these services independently. There's also a dev and demo environment that you can get from this GitHub project. It's in a particular branch, and it is still under active development. As I mentioned, we're sort of in the middle of the 2-year grant. It contains Docker support infrastructure, and it comes in 2 flavors, a Docker flavor and a sort of direct Java jar flavor that you can embed in another environment. All right, well, I talked a lot, so I would like to see if there are any questions that I might be able to answer. And of course, if this sort of exceeds the scope of the time that we have left for today, I will be more than happy to take your contact information or talk to you in the hallway or take this offline. Yes?
What language is LOCKSS in going forward?
So we are going to remain mostly in Java. So the original code base is 1,100 Java classes. I mean, it's a sort of a huge application with many different things, including parsing various formats that are of interest to libraries. I mean, it just came with a lot of baggage. And cracking that open has been an interesting effort. It remains mostly in Java, but if I go back to this diagram, so for example, what's an example that I could show you here? So inter-process communication nowadays, it used to be this monolithic LOCKSS stack all in Java, and so it was just easy for any component to communicate with all the others, all inside the same memory space, all inside the JVM. So now we need a message service of some sort for inter-process communication that does not have to be any particular one, right? I mean, there are several choices. The databases no longer have to be all Java embeddable. It could be a database of some other type. Moving forward, the core of the LOCKSS system will most probably remain in Java because that's what we've written and that's what the team at Stanford University and Edina in Edinburgh, Scotland knows best. But over time, it's not unlikely that you'll start to see sort of like other applications as people make them available that plug into these REST APIs but aren't themselves in Java. Yes, same.
The service is going to be containerized?
Well, they can be. So, I mean, so all of these sort of the blue ones here, all of the blue boxes are currently available as sort of a Maven Central jar, right? A sort of a standalone jar, which you can then embed in various ways that suit you. And then that jar is also available as a Docker container that runs on its own. This was not so much of a sort of like an endorsement of Docker technology over other containerization, but that was just as good for us to get started in this sort of new environment where the components might not be living on the same machine or on the same host, right? The storage system might be on one machine, right? More akin to what universities and large data centers have today, which is not an appliance model where sort of like there's a pizza box in the rack and it does everything LOCKSS, right? Nowadays, the storage, the database, the metadata extraction, the replay might all be totally different hosts. So right now, Docker containers are available. Well, I'd like to thank you for coming to see this presentation, and I'd also like to thank SW in particular for inviting me. It was a very interesting experience being closer to industry. I've been in academia for a long, long time, sort of in this niche application, and it's very interesting for me to meet other storage-minded people that have very different interests than me. So I look forward to conversations in the hallway.